Hi everyone, my name is Santiago Aguado-Montero. I'm a PhD student from the University of Seville in Spain, and today I will be presenting the work entitled Experimental and Numerical Analysis of Fatigue Cracks Emanating from Internal Defects in a Selective Laser Melted Titanium Alloy. This is the index I will be following. After a few introductory comments, we will analyze the experimental work that serves as a basis for the present research. After that, we will discuss the numerical model proposed to simulate the situations considered in the experiments. Next, we will attempt to match both experimental and numerical results. When compared with conventional manufacturing processes, such as forging or casting, additive manufactured parts exhibit four main differences that drastically change their mechanical behavior. First, it is well known that selective laser melting imposes a very bad surface finish in the fabricated parts, as can be seen in Figure A. This terrible surface finish can, for example, enhance surface crack initiation, acting like stress concentration points. Second, the high cooling and solidification rates that take place during selective laser melting fabrication give rise to the appearance of very fine microstructural patterns, usually following the melt pool shape, as observed in Figure B, resulting in a very particular grain structure which is quite different from the one produced with any other manufacturing method. Third, the successive, very localized heating and cooling cycles imposed by the metal-laser interaction result in incompatible thermal strains that need to be accommodated in the form of residual stress or, in the most severe situations, macroscopic delamination or cracking of the specimen, as depicted in Figure C. Fourth, different mechanisms such as gas entrapment, keyhole collapse, or lack of fusion can promote the appearance of internal defects. While the first two cases are usually associated with spherical voids, lack of fusion is linked with the presence of very sharp, crack-like defects left in the material. Figure D shows a longitudinal cut containing the building direction of a specimen, where an example of the first type of defects, an almost spherical one, is shown. We can also observe in this figure the very high surface roughness that was present in the specimen. In the present work, we analyze experimentally and numerically the effects of residual stresses and internal defects on the mechanical resistance of a titanium alloy manufactured by selective laser melting. For now, we will not consider the effects of neither surface roughness nor microstructure. The test specimens considered are prismatic in shape, with a cross-section of 22 × 10 mm and a length of 80 mm. All specimens were built in the vertical position and received residual stress relieving and sandblasting. Additionally, they were subjected to either shot peening or laser peening. We are interested in studying the evolution of cracks emanating from internal defects, which is usually the case in both shot-peened and laser-peened specimens, due to the compressive residual stresses left close to the surface, promoting crack initiation inside the part. The residual stresses left in the material have been measured and can be observed in this slide. Fatigue tests were carried out in a 4-point bending setup, as schematically shown in the figure, with rollers separated by 15 and 70 mm, respectively. When we observe the fracture surface with the naked eye, we observe a very bright elliptical region barely touching the surface of the specimen. When analyzed with the microscope, one can notice the presence of a relatively large defect inside this bright region, which can be assumed to be the critical defect, that is, the defect that the crack initiated from. In this particular example, scanning electron microscope image of the critical defect can be observed in the bottom left-hand side. We hypothesize, and we will try to prove this via numerical simulation, that this elliptical bright region shown in the top left-hand side figure is related to the shape of the crack right before it reached the free surface, transitioning from an embedded to a superficial state. And as I said, we will try to prove it later. As we move outwards from the defect, we observe four different regions in the fracture surface. The first few hundred microns show a microstructurally textured region that clearly follows the typical acicular martensitic texture of a titanium alloy, as shown in the figure labeled A. According to related bibliography, this is a consequence of the crack evolving under a stress intensity factor just above the fatigue crack growth threshold. As we increase the distance from the defect, we get deeper into this elliptical bright region where no particular texture is observed, as posed in figure B. This can be a consequence of the two sides of the crack crashing against each other multiple times, erasing all crack front evolution information. If we continue moving farther away from the defect, more and more striations are visible as we progressively get out of the bright region, as shown in figure C. It is important to note that no drastic transition is observed, but rather a very slow increase in the amount of striations observed. Last, we find the final fracture region where a typical dimpled surface can be observed in figure D. If we have a closer look to the critical defect, we can make use of both scanning electron and confocal microscopy to determine its whole three-dimensional geometry. In particular, apart from obviously quantifying the projected size of the defect, we can analyze both sides of the fracture surface with the confocal microscopy, match them and obtain a vertical profile of the defect cross-section, as shown in the bottom left-hand side figure, where the z-axis is perpendicular to all three microscope figures, and the x-axis is represented by a white line in the bottom right-hand side figure. Thus, we can determine whether the defect is blunt or crack-like, and quantify the notch radius. In this particular example, we find a surprising result. Instead of being a blunt or a crack-like defect, we see a combination of both situations. Now let's try to build a computational model to numerically simulate a situation that is similar to those in the experiments discussed before. We will be using a complete initiation and propagation model, which I will not explain into much detail since that has already been done multiple times before by authors such as Jaime Domínguez, Carlos Navarro, and Jesús Vázquez. In a nutshell, typical initiation and propagation models require one to choose what's called the initiation length, which is the length the crack has by the end of the initiation phase. This selection is rather arbitrary, so some controversy appears. The model used in the present work allows one to calculate fatigue life as a function of that initiation length, and by the end of the process, we can choose the most conservative result. This model has been used several times before, yielding very good results. Let's focus on the propagation phase, which has been slightly modified for the present research. In order to calculate the propagation life, one needs to compute the stress intensity factor. This was done making use of a weighting function methodology. It must be pointed out that the crack is defined as the summation of both the actual cracked region surrounding the initial defect plus this initial defect itself. So the defect is part of the crack. Initially, we tried to use a crack growth law as the one shown in equation 1. This crack growth law is of particular interest because it takes crack closure effects into consideration by using the Newman's F parameter. However, this crack growth law failed to provide successful simulations in the first place, since many runouts were predicted, which did not match the experimental results. To solve this issue, we considered that in Newman's work, the crack analyzed has been obtained by a crack growth process. In this situation, crack closure mechanisms have fully developed. In our case, the crack in its initial state has been directly manufactured in that configuration, so we can assume that no crack closure is present at the beginning of the fatigue test, but instead this needs to be progressively built up as the test goes on. For this reason, we multiplied Newman's F parameter by a function that goes from 0 to 1 as the crack evolves from its original state. The variable controlling this crack closure buildup is the distance traveled by the crack front, measured from the initial state. The approximate distance required to build up this effect was assumed to be in the order of the El-Haddad parameter. This assumption obviously requires further research, which will be done in the near future, in order to determine the exact distance required for the crack to reach a steady state situation. In the present slide, we observe simulation results for different models considered. First, it must be pointed out that circular icons represent crack-like defects whose initiation life was not taken into consideration, and they were considered to start propagating right away. On the contrary, triangular icons represent blunt defects, simulated with the complete initiation and propagation model. First group of data, depicted in blue, represents the simulations obtained by making use of the simplified crack growth law, which does not account for crack closure developing effect. As stated before, this crack growth law predicts too many unexpected runouts. On the contrary, black icons represent simulations computed with the complete model proposed in the present work, yielding more accurate results. Furthermore, if we make use of this more complex model, we observe that calculating blunt defects as if they were crack-like does not significantly change predicted fatigue life, as can be observed if one compares black and red triangular icons. Note that this would not be the case if the simplified model were used, as represented by pink triangular icons, all of them predicting runouts. Considering all defects as crack-like is a very useful approximation, since calculating the complete initiation and propagation life of a blunt specimen requires a significantly higher computational effort compared to a simple propagation calculation. In this last figure, we can observe the final results, obtained with a complete model that takes crack closure evolution into consideration and assumes all cracks to be crack-like. Only one unexpected runout was predicted, and two of the simulations resulted in a life slightly shorter than experimentally observed, possibly caused by errors in defect characterization and residual stress measurements. The rest of the simulations provided quite satisfactory predictions. Finally, we attempted to simulate not only the fatigue life, but also the crack front evolution. In particular, the process by which embedded elliptical cracks approach the free surface of the specimen and turn into superficial semi-elliptical cracks is of great interest, since most of the specimen's fatigue life was associated to embedded elliptical growth, and thus this transition from embedded to superficial crack usually means that final failure is very close. In the present slide, we can see 4 different tests that were simulated by making use of the complete model previously discussed. In each of the figures, 3 items are drawn. The yellow ellipse represents the bright elliptical region of the fracture surface that was measured experimentally. The orange ellipse represents the shape the crack had just before transitioning from an embedded to a superficial state, according to the numerical simulations. Finally, the red curve sketches the residual stress profile in each case, providing some insight of the length scales. As can be observed in the figures, most of the simulations allowed for a very good correlation between the elliptical bright region observed experimentally and the numerically simulated crack in the embedded to superficial transition. While most of the cases provided very little errors, 2 of the simulations could not be completely matched, resulting in graphs like the bottom right-hand sided one. However, even in these situations where the size of the ellipse is not exactly captured, the general tendency, particularly the aspect ratio, is still comparable. To conclude, in the present work, we analyzed experimentally several fracture surfaces of a titanium alloy fabricated via selective laser melting, and a common pattern of 4 different regions was observed in these fracture surfaces. Also, the critical defect initiating the crack evolution was localized in the fracture surface and quantified making use of both scanning electron and confocal microscopy, so that its shape and character, that is, blunt or crack-like, were determined. In order to attempt for a numerical simulation of fatigue crack growth, we developed a crack growth law considering crack closure evolution, which eventually led to satisfactory simulations. Furthermore, we came to the conclusion that assuming all the defects to be crack-like was a useful approximation. Finally, fatigue crack evolution was correlated to the observed fracture surfaces, and one of its regions, a very bright one, was matched with the shape of the numerically simulated crack during its transition from an embedded to a superficial situation. Finally, we present the main bibliography consulted during the present research. Thank you very much for watching this video presentation. Have a good day. Bye!